Hi class, this is Mrs. Juliana again here to do review part 2. So review part 2 for unit 4 test. And the first one that I want to do is number 8. Number 8 says use the approximate half-life formula for the case described below. Discuss whether the formula is valid for the case described. All right, so urban encroachment is causing the area of the forest to decline at the rate of 7% per year. What is the half-life of the forest and what fraction of the forest will remain in 20 years? So we're talking about half-life and decay, and approximate half-life formula is 70 over P. So we're going to first find the approximate half-life formula. So 70 over P, where P is what? 7% per year. So it's just the percentage 7. So that's going to be 10. All right, so that's going to be your approximate half-life of the forest. The second thing it asks us to do is report what fraction of the forest will remain in 20 years. So in 20 years, that means little t is 20. And when we do this type of problem, we put 1/2 in the calculator and then take it to little t over half time, and half time is 10. So little t is 20 and half-life is 10. So that just means 1/2 to the second power, which is 1/4, or 0.25. So I just have to remember that when I get out of screen capture here. So 10 and 0.25. So the half-life is going to be 10 years. And then the fraction will remain as 0.25 after 20 years. Alrighty. Next one we'll do is number 9. Oh, we do need to answer, is this formula valid? And we would say probably yes, because 7% is below 15%. So there we go. All right, next question. Use an annual growth rate of 1.4% in a 10-year period for a certain population to find the approximate doubling time and then predict the population in 2050 based on the 2000 population of 5 billion. All right, so first thing we need to do is find an approximate doubling time. So approximate doubling time is going to be 70 over P, which is 1.4. And that's our first thing. So 70 divided 1.4 is 50. All right, so 50 is your doubling time. And then we're predicting the population in 2050. So we take 2050 and subtract 2000 to come up with our little t, which is 50. So our little t is 50, doubling time is 50. And if we have a population of 5 billion, we're going to multiply that by 2 because it's doubling time to the little t over doubling time, which is 50 over 50, which is just 1. So that means 5 times 2, or 10. So 10 billion will be the population at that time. All right, so what is it, 50 and 10? Oh, 50 years. It's a doubling time, and then we found it to be 10 billion for the new population. 50 years have passed with that formula. Awesome. All right, number 10. So the following table gives the birth and death rates for 4 countries in 3 different years. Find the growth rate due to births and deaths in each of the 3 years for country A. So we're just looking at country A, and I'm going to just go ahead and highlight that. So we're just looking across here. And then birth and death rates. So our birth and death rates are going to be, you're going to subtract them to come up with your growth, your net growth rate. So 1985 and 1995 and 2003 will have their own little years. So 1985 will be 14.4 minus 11.7. 1995 is 10.9, subtract 11.6. And then 2003 is 9.8, subtract 11.3. And those are going to be your net growth rates for each of those 3 years. 14.4 minus 11.7. I'm just going to put these all in my calculator and then extract it after I get out of my screen capture. So 2.7, negative 0.7, negative 1.5. Now, you'll notice probably that this is a negative growth rate, so it's going down 2.7 to negative 0.7, and then it reduces again to negative 1.5, so it's in decline. So what might happen is the country is going to decrease in population over those years. So I have those in my calculator, so I can type them in. So the first was 2.7, and the next was negative 0.7, and the next was negative 1.5. All right, so those three were the year's growth rate. And then it asks us what's going to happen, and the country's population will decrease based on those growth rates because they're getting more and more negative. So that should be our final answer. All right, next one is number 12. It says, in the following situation, state whether two variables are related in a way that might be described by a function. If so, identify the independent and dependent variables. You walk through a used car lot and list the price and model year of each car you see. So are they related for a function? And it says determine, so you walk through a used car lot and then list the price and model of each car you see. So price and model. Can the situation be described by a function? This one's kind of a rough one. I'm thinking it cannot be because they're going to be all over the place and we would need it to be linear, whereas some model years I just don't think they're related linearly. Yep. Oh, good job. All right, next one is number 14. All right. Write a short statement that expresses a possible relationship between the two variables. And they say travel time from Denver to Chicago and average speed of car. Possible relationship. So it seems like if you're driving from Denver to Chicago, the faster you go, the less your travel time will be because you're getting there faster. So as the time to drive from Denver to Chicago increases, the average speed of car increases. So the time is independent, whereas the speed is dependent. So let's see, average speed of the car increases, time is going to decrease right here. I'm guessing C. As the time increases, all right, so I think that's right. Let's check the answer. All right, so it is that the average speed of the car increases and then the time will decrease because the faster you go, like I said earlier. All right, I need to repeat myself. Number 15? Yes, number 15. Consider the graph of the function below. Identify the independent and dependent variables and describe the domain and range. So I'm going to push this down a little bit. So you're clicking to describe your answers, of course, but we need to see this x-axis, and it looks like years are along the x-axis, and we start at 1950 and end at 2000. So the independent variable will be years, and the dependent variable is the population because it's along the y-axis. It's the range there. All right. And then the domain of the function has to do with, in the function, where does it go from 1950 to 2000? So, whoops, years, I'm going to take years. So the domain of the years from 1950 to the maximum of 2000, because those are the years that the function encompasses. And then the range is going to be the populations. And then the minimum value for population is, and it says the nearest integer, so we're going to have to go to 2 down there because we're a little more than 2, but the nearest variable is 2. And then 6 is the highest. That's an integer. All right. And then choose the correct description below. The function shows a steady increase in population from 1950 to 2000. The function shows that there has been a relatively constant world population since 1950. The function shows an initial increase in the population, but then a decrease. Well, the last two are definitely out and will be in C. And then D, the function shows the rate of increase in population has been increasing since 1950. And it has been increasing, but the word steady is kind of important because it's almost linear. That's pretty steady. So we want to make sure that not only, and it's kind of weird to say the rate of increase in the population has been increasing. The rate of increase is increasing since 1950. I think it just shows a steady increase in population. All right. And then 17. So we're going to move over to number 17 here. The following situation involves a rate of change that is constant. Write a statement that describes how one variable changes with respect to the other and give the rate of change numerically with units and use the rate of change rule to answer any questions. So you're running along a path at a constant speed of 4.2 miles per hour. How far do you travel in 1.9 hours and 3.6 hours? First of all, the statement is that you are running at a constant speed of 4.2 miles per hour. So we need to look over here and figure out which one of these is stating that. The first two are out because they are in hours per mile. So those two are out. So we need to look at the last two only. Time varies with respect to distance traveled with the rate of change of 4.2 miles per hour, or the distance traveled varies with respect to time with a rate of change of 4.2 miles per hour. Which one would you think that one is? And it varies with respect to time, or not it, but distance varies with respect to time. So we're going to choose T. Okay, so your distance that you've traveled is changing as your time changes. And then we have to state what is the distance traveled after 1.9 hours. Now, I don't know if I can screen capture, but I will. So if it's 1.9 hours, we have to multiply our rate of change, 4.2 times 1.9. And then the second one is going to be our 4.2, which is our rate, times the time, 3.6 hours. All right, and remember our formula, distance equals rate times time, and that's why we're going to multiply rate times time together to get the distance in miles. All right, so 4.2 times 1.9 and 4.2 times 3.6, and we have 7.98 and 15.12. All right, and I'm just going to get out of here, type them in. So 1.9, it says type an integer or a decimal. All right, so 7.98, I'm just going to put in. Oh, I put it in my calculator. 7.98. And then the last one was 15.12. All right, that's how you would do that problem. And then what is the next one? Do I have time for one more? It is 18. Well, it's going to take a while, more than a minute. So I'm going to stop here, and then we'll start at 18 on the next slide or the next video. Have a great day. Let's see.